Okay, welcome everybody. This is lecture 5 on invariant maximality reversal, please.
Thanks. I This is the fourth one on the reversal, and we decided to go backwards. So this is 10. If I remember right, 11 minus 1 is 10. So that's where we are. Um, and Just to quickly review what's going. Oh, by the way, yeah, no, I saved this down here. Yeah, the text of the previous lecture is at my downloadable lecture notes page. It's later than I promised, and the previous lecture notes, and then and that's on section 411 of the reversal, the last section. Also, the current version of section 411 in full is on my downloadable manuscripts page. Now let's recall we were reversing this statement. Keep this goal in mind. We're reversing this statement to con SRP. And the the table of contents of this chapter 4, which is the reversal, is here, not changed. And 411 was last time, and now we're doing 410. Uh, Now, I have to start with the end of section 4.9, just like when I did 4.11, I started with the end of section 4.10. So I want to start with the end of section 4.9 and then proceed. So the end of 4.9 introduces a structure X, uh, which is a second order structure. Um, it differs from the second order structure in the last lecture. And I'll explain the difference. But this one is earlier, and it has the same. Well, no, it doesn't have quite the same form. Okay, so um, we have a strict linear ordering on D with the least element, where every element has an immediate successor. This is an internally well-ordered system at the end of section 4.9, an internally well-ordered system with constants C1, C2, and so forth. The U's are going to be subsets of uh, of set. Okay, set is a family of subsets of D. So it's a second order system. Of course, we wouldn't dare have all subsets of D. Of course, we have only countably many. As expected. We have the constants are strictly increasing with no upper bound in D, and we have unary predicates on set, or if you like, just subsets of set. U1, U2 that increase, where every element of set lies in some UN. And these UNs are, so to speak, kind of in and around the constant Cn. Whereas they're subsets of some number, some place below Cn. There are certain subsets of places below Cn, you see, in number 4 here. And then we have pair is a ternary relation, which is the graph of a bijection, which satisfies the recursion equation. Well, it satisfies the inductive definition of pairing. Less than sharp is max lex. I call it max lex. So you order pairs by taking first the max and ordering them, and then if they have equal max, you order by lexigraphically. And this is required to be dominating, greater than or equal to D1, D2. Also, f of 0 Cn is Cn itself, and it maps each 0 Cn right open into 0 Cn right open. Um, and it's order preserving. In other words, if D1, D2 is Lex max less than D3, D4, then F of D1, D2 is less than F of D3, D4. And you have ontoness. Okay. Then we have internal well ordering. In other words, every non-empty element of set has a least element. And supremum, every element of set has a less than D least strict upper bound. And then we have separation and indiscernibles. All through the book, we always have separation and indiscernibles as the involved axioms, so to speak, that evolve and get stronger as the reversal chapter progresses. So we have a. I'll describe this language L of x n minus one m below. But if you have a formative phi and you have uh, parameters d2 through dn that are points and parameters that are sets, the parameters that are sets have to be in this u of n minus 1, which is sets associated with c of n minus 1, actually, that when you form this comprehension or separation, you get a set that's in u of n. That's in u of n. Uh, okay. One of the things I'm going to check carefully is why I didn't uh, say this stronger. A1 through ANB and U of N. Well, there's probably a technical reason why I want to make it weaker than that, but that's not important because N varies, from N varies, so it's not doesn't look like real much of a too much of a difference. But I do it with U of N minus 1. I have to look into that. I don't like to have weaker statements than I should have. Um, okay, so and then we have X indiscernibles, but the number K that we use throughout this entire reversal. Remember, there's a number K that's used throughout this entire reversal. It's a large integer, and it's a parameter with respect to everything we do, including this statement. This K appears um, in the form of the complexity being at most K. So we have a formula of complexity at most K uh, with parameters less than C of R and point parameters and set parameters in U of R. And then we want to give an order preserving change in the indices I greater than or equal to R, uh, for which C of I or U of I appear, staying within R through n minus R, n minus 1. Then uh, we get equivalence of the set. We get equivalence of the set. Okay. So that's the form that the indiscernibles take. All right. Now, if you remember last time, remember we're going backwards. Last time I was using $n, I wasn't using U of n. And $sign of n incorporates constructibility. So the main event in this today in section 10 is to develop constructibility within our system. I mean, this system is the reason. Within this system, we want to develop constructibility to create the new system, the later system on which we based the last lecture. And what will happen is that $sign of n at something at a set will be less than C of n if and only if that set is a member of U of n. Except that's not quite, that's a lie, a little bit of a lie, because I'm not talking about constructibility, but that's the idea. Uh, okay. We can recover the new U of n from $n. The new U of n, of course, is a substructure. It's the constructible elements. All right. So about this language, it's the fragment of the language of X, the structure we're talking about, which is the formatives whose constants are among C1 through Cn, whose U's are among U1 through UN, and whose variables are among D1 through DM, A1 through AM. So we only have finitely many variables here, and the assignments are when D1 through DM is less than D, and the sets A1 through AM are in UN. Okay. So now that, just reviewing this for a second, just glancing at it, this is the end of section 9 and the start of section 10, uh, this structure X, this second order structure X, with its indiscernibles and uh, its internal well ordering, its indiscernibles and its separation and indiscernibles. With the indiscernibles are limited to complexity K, but the separation isn't. That's a, obviously that's something that section 9, which is next week, spends a lot of time getting limited separation and shape in this nice shape. All right. So we got the language. Now, internal constructibility. Okay. In theorem 4917, we defined a structure X explicitly using the explicit definitions of its components made in the structure M. Um, oh, yeah. Yeah. Let me tell you what this is talking about. I just was talking about structure X. Now, structure M is from the previous section 4.9 and 4.8. Section M, excuse me, the structure M um, has the number K more heavily embedded. Now, we're not going to talk about the structure M because that's the next lecture, because we're going backwards. Uh, but that parameter K was arbitrary, but at least 2 to the 2 to the 2 to the 1,000. That's what that number is. That's a pretty big number. I just put something down that was safe. It's not important. Um, Now, the number K in what we just talked about only appears in the indiscernible axioms, X indiscernible sub K. And our first order of business in this section 10 is to liberate ourselves from this parameter K once and for all. So we get into a much more normal situation. Um, Now, in order to do this, we have to do things a little differently. Uh, Theorem 9.917 says that the constants C1, C2, C3, and so forth are cofinal, but that's not a first order assumption. So we want to move this into first order and apply compactness. So uh, we have to weaken this theorem 917 that we just went over. We have to weaken it uh, to simply say that some structure has a model. That some structure has a model. And obviously that's weaker because you can't say that constants are cofinal in a first order way. Okay, so um, all right, so here's what we do. We have to weaken, just that's what I was saying. Also, elements of sets, you can't write that they're the union of the UNs because that was all would also not be first order. Okay, so actually, we'll write some of this out, but not all of it. It's a little bit, as a strict first order theory. So there's a structure X satisfying the following set of sentences in the language of X. So a lot of this is just copied the same. Less than is a strict linear ordering with at least extensionality. Um, ah, so the constants are strictly increasing, and um, the UNs are strictly increasing. Maybe this is UN. Maybe this is not. Maybe this is meant to be maybe a predicate, a univariate predicate. So maybe I should write it this way. Yeah. Yeah, maybe all through this I should. Oh, then I wrote this way. That's not right. Yeah. Okay. Yeah, just to be a little bit more formal about it. Yeah. Okay. Pair is a ternary relation. Now here, this is clearly first order kind of thing. No problem. I mean, this is a scheme. Yeah. This is a infinite set of sentences. Yeah. X well order is one sentence. X supremum is one sentence. Now limited separation um, is infinitely many sentences because I don't put a bound on the complexity. But so it's infinitely many sentences, not changed from what it was. Um, okay, X indiscernibles is just copied from where it was before. All right, I'm not going to continue to write this as a unary predicate anymore. We've grown out of that. Uh, so this is the same, and it's a scheme. But, and it's actually not a scheme, I guess, because the complexity is in most K, any complexity measure will do. So that there's only finitely many formulas of a given complexity. Obviously, that's what we want. Um, yeah, so I guess that this is actually finitely many axioms. Yeah. All right. Now, this reworking of 4917 still uses our K, of course, in the X indiscernibles K. And this is a trivial weakening. This is a weakening of the previous, right? Okay. I say that this has a model. That's all I'm trying to say. Just trying to say this has a model. There's a structure satisfying. Yeah. All right. Note that the axioms 1 through 10 strengthen as we increase the parameter k greater than or equal to 1003. Yeah. So by the compactness theorem for two-sorted predicate calculus with equality, we obtain the satisfiability of the union over k of the set of sentences. So now we have the same thing copied completely. Isn't it nice to have uh, copy and paste? Except that we don't say in X indiscernibles anything about being of complexity at most K, just everything, right? The miracle of the compactness for first order logic and its variants. All right. So now we finally have released the long-standing parameter K. Get a good riddance. All right. I mean, K played an enormously strong role in the beginning. Everything you could see had a K in it. Then it started to be a little thinner and then thinner and still thinner, and now we got rid of it. Now, we do have to remember, though, that we've got constants C1, C0, C1s that don't go to the end, may not be cofinal, and we got U's, U1, U2, U3, that may not be uh, uh, cofinal in SET, the family of all sets. All right. But we got to be able to quantify over SET. We got to be able to quantify over the entire universe. Actually, we could probably get away with localizing things, but it's not, but it would be ugly. There's no reason to do that. You just have to do what I said. All right. Now we're going to use P instead of pair. We're going to use P as a function. We're going to work in this system X. This system X that we just without the K, this system X is where we're working the entire today. Yeah. We use less than instead of less than D, P instead of pair. The elements of D, by the way, you think of the elements of D as internal ordinals because we have this well ordering stuff. Okay. The main goal of this section is to build the internally constructible hierarchy of internal sets of internal ordinals, L, an inner model of X and analogous to the constructible sets of ordinals in standard set theory. Set is replaced by L, and L will inherit limited separation X and X indiscernible. So, in other words, we'll really have the same basic principles, except we're going to have dollar signs that you saw in last lecture. That dollar signs are going to appear. Uh, yeah, it's section 11. Well, now, this is talking from the past. So in section 11, what we did is we converted L to a model of SRP, if you remember, by converting flat set theory to ordinary set theory. All right, so we have some triviality, some easy stuff first. That pairing, I think that may be even just almost a restatement of an actual axiom that we put down for W, that CNs are closed under pairing, and CN is a limit. That comes from the easiest kind of indiscernibility, the kind we're talking about. Uh, there's a least limit ordinal because we have internal well ordering. If there's a limit, there's at least one. And since C1 is a limit, right? Uh, do we start numbering from one or zero? I don't know why I would care about this, but we start numbering from ones. Yeah, one. Okay. Indiscernibility again. Then we get that. And then we get unique successors and right minus one of E exists. And then we have before omega, we have D minus one is less than omega. Yeah. Obviously D plus one also, because it's a limit. But you actually get this too. Because omega is the least limit, you get this. Because omega is the least limit. All right. We don't have to get into detail about this. Straightforward. Okay, now we need a closure. So D is P closed if and only if it's at least omega, and it's closed under the pairing operation. Now, in ordinary set theory, this would close. The P closed corresponds to being a double power of omega because you're talking about being closed under multiplication. So yeah. Okay. Now each CN is P closed, and for all D less than CN, there exists a P closed. In other words, a CN is a limit of closed. Now we're not going to spend all our time just stating these trivialities. We just need a certain amount of this. And I don't want to develop ordinal arithmetic. There's no need to develop exponentiation here, though we could do it, no problem. There's no need to do that. We just need some specific thing like this. Um, CN is P closed because of indiscernibility, and D less than CN, there exists P closed in there because if you had the greatest one, you'd also, being smaller, you'd also violate an indiscernibility. Now, we want to smoothly work with multivariate relations, not just sets. And I don't want to, develop a whole big deal notation and so forth. We just proceed pretty informally, semi-formally. But we use the fact that pairing functions iterate as normal, left associative extension, so to speak. Yeah. Here's R where this here R is standard. All right, then U of NR consists of so we already have U of N. We have U of NR consists of the E's such that the forward image of the R area pairing operation, the R area operation forward image E is as a one-dimensional set is in U of N. I don't know if I need to do things less than infinity. It's kind of nice to have it, but it's not really important. But I do it. I do it anyways. Is the union over N of UNR? And remember, N is standard. N is external. U of N less than infinity is the union over R of UNR. U and less than infinity. Yeah, I don't think this is really needed much, but it's natural. All right. If D1 through DR are less than Cn, then P of R of D1 through DR is less than C of N. In other words, C of N is closed under under R area stuff. That follows trivially from being P closed. And the other way is uh, also easy because remember the pairing is a dominating function. It's a dominating function. You get that, Matt. Uh, and E is in UNR if and only if P of R of E is a member of U of N. So one direction is the definition, and the other is easy consequence. Uh, yeah. Okay. So this is basic. Now, in limited separation, this is the kind of thing I don't want to get too much detail. You can generalize our limited separation when we have arity, and we can generalize the U of JR instead of just using the U of J. So I have some noise here about how that's done. Why is that? You have to expand that out so it doesn't look much different than U of J with some first order stuff, with some very definable stuff so that nothing bad happens to you. All right. For X indiscernibles, we argue similarly replacing the U of J R with the U of J, just to expansion out. Make free use of this multivariate limited separation. Uh, yeah. Now, we also want to enumerate the P closed points. That's like enumerating, uh, that would be in set theory like enumerating the double exponentials, which would really be a matter of actually developing the exponential function. But we don't want to go that far. We just want to do this, which is very basic. Um, it's a function which is starts as omega and goes up uh, by f, where f d prime is the strict soup of the f double d prime less than d. Now, why didn't I just mean to apply this to closed points. Uh, yeah, f of d prime plus one is the least p closed point greater than uh, f of d prime. Yeah, that's what we want. So we have to know this is what a de-enumeration of p closed points would be. And I call it a de-enumeration because the domain is the points that are less than d. So we want to prove that this makes sense, that there is such a thing. We're working within a structure W. We want to know that there is such a thing, which is in capital U of somewhere, right? If you're going to do this, well, you'll see what I'm saying. Lemma 4, 10, 7. Let D be less than C of N. Any two D enumerations of P closed points lying in somewhere in the U's are equal. Every D enumeration lying in the U's is actually lies already in U of N2, where N is associated with this same N. Okay. Now, this proof is done just like almost everything in this section, um, where we take the least, you want to do something for a long time, you take the least place at which you can't do it up to there. And that's defined, that's nicely defined. And then you take the union of the approximations, and that's defined. It's not defined as well as you'd like because it actually mentions Cn plus one. See, it's not defined as nicely as you like, but then you use indiscernibility to argue, since it's made of lower stuff, you use indiscernibility to argue that it is defined nicely, and then you have a contradiction because it was supposed to be impossible to go that far. So we're going to do, it just goes on and on like this forever in this section. You want to do something for all the way up to CN or something. You want to do it. You say you can't do it all the way. But you want to get a contradiction, which means there's a least place where you can't do it, and that all lives below CN. Least place where you can't do it, and then you say, "Oh my God, I can do it," but it's going to be defined somewhat higher up than where I'm at, and then you argue that, well, then it can be defined the way I wanted it because of indiscernibility. The C's can come down and the U's can come down. And then I got my contradiction, which means I could have always done it. Let me just say this once more, slightly better. You want to do something defined nicely. You want to do something defined nicely over, say, all of CN. You say, well, let's look at the least place where I can't do it nicely up to that place. I can't. Then you argue that I can do it not as nicely as I want, but somewhat nicely because can define this all. I can define this all involving involving the definability I wanted nicely. And then you argue by indiscernibility that you could then do it nicely, which is the contradiction, which means that you could have always done it up to any place. All right. That's how indiscernibility and separation conspire together to do nice things. That's how it works. All right. So we get a unique de-enumeration F of P closed points, uh, F in U of less than infinity 2. This F is in U of N2, and the sup of the range is less than Cn. With another indiscernibility, you get that too. All right. So this is as expected. And then often, as you know, these are breaking into successor, basis, successor, and limit cases, where the limit case is the only thing that has any obstacle, and then you have to use indiscernibility. All right, D star. Yeah, I don't know that I need to do this, but D star is the union of all the zero CN. Remember, it might be a cut. It might be a cut in the D. It might be a cut. And P star is the union of all D enumerations of P closed points over D in that cut. I don't really think it's important, but I think conceptually it's probably a good idea to do that. And then um, and then we have a strictly increasing function, P star. Okay, lemma 41010, induction. Every non-empty bounded subset of zero omega. Now this is the omega, the non-standard omega least limit point in the structure W. Non-empty bounded A lying in U of less than infinity 1 has a maximum element, right? And that comes from limit point and well, that comes from the supremum axiom, yeah. All right, fine. Now we want to develop omega recursion. Okay, omega recursion, like in primitive recursion, except that we're in a transfinite, not standard transfinite setting. Everything's though internal, first order, and everything. Uh, and the way to do this is to first treat omega recursion of length any given internal number S. So we're going to have length S, length S recursion, where S is an internal number. Not well, if S was an external number, there's nothing to prove. It's when S is an internal number that we care about. And I formally define what I mean by omega recursion. You have to be a little careful what you're talking about, but it's straightforward. Where the ingredients are in the U's, then there's a unique map. You see, it's the map. This map is a kind of length S. You see, in other words, in the cross sections we have S different functions, um, such that the basis case and the successor case. But the length is only, and I want to claim that we get something in the same U of N. All right. R and N are external, and external means standard, and I and S are internal. Um, and this is proved by an induction. Uh, I don't actually quote the induction. I actually redo it. I think that's not optimal. Okay, but the idea is you're doing induction on S that these things exist. Um, and then you have to argue that the function at the end, which is a length S function, so to speak, is in fact in U of N R plus 3. I think this could all be redone. I mean, I do it almost from scratch, but I think it'd be redone by talking about induction more than I did. Uh, but we use indiscernibles. But we use indiscernibles probably to do that induction also. Yeah. All right. Maybe you don't just quote induction here, but you take the least place at which you can't do this, you see. And now we have no limit case because S is an internally finite number. There's no limit situation. So this is probably, uh, but again, we use indiscernibility because uh, yeah. Maybe I'll take a look at this, maybe simplify it, but I think it's all right. But now we have the full recursion that we need. Uh, and and this is just a matter of this is instead of little s, we use, here, capital omega. You see where you go through all the we do that because we can put together all the ones we did with little s. Remember, you can prove they cohere by induction. So you put them all together. Uh, uh, and if you do this, then you wind up with something here with n plus one, but then you pull it down by indiscernibility. See, you form the union H. You see, H is only in there. You see, because we're unionizing things uh, where we're mentioning, we're quantifying over all of U of n. We're quantifying over all of U of n when we unionize this in the separation. So that means we're in U of n plus one, and then you can pull this down because of the indiscernibles. Okay. Now we introduce the inverses of the pairing function, first and second coordinates. And this is a bijection, so the inverses are nice and all that. And we're going to use the inverses a lot. So use the inverses heavily. So we got to know something about them. Obviously, they're regressive. And when I restrict, I'm in a U. Uh, yeah, maybe I should say uh, this is what I want to say. All right, let's just leave it like what I was doing. Then I have to, then I have to say then less than infinity, right? All right. Yeah, this is just limited separation. There's not even any indiscernibility involved. Yeah. Yeah, separation in the right way. Yeah. Uh, yeah, because the separation allows pairing, and then F and G are defined trivially from pairing. Yeah, so I think that's all right. Okay, we now implement finite sequence coding using F and G. Using omega recursion, we make the following definition. Yeah, finite sequence coding is very important. Now, we're not talking about standard length finite sequence coding. That's nothing. I mean, that's not much, excuse me, because we have inverse pairing. What's trickier is we want to do finite sequence coding where the length of the finite sequence is a non-standard integer in the model, in the W, right? We need to talk about that. So uh, we need to be able to iterate a nice function nicely. We want to iterate a nice function nicely finitely many times, where the number of times is a non-standard integer. Yeah, this is iteration right here. It's a non-standard, it's internal, and we use omega recursion here to do that. So this is pretty clear uh, that this is just a special case of the omega recursion we just did. There's nothing really to do. But now we want to define the code. So what's the ith term of D? What if I view D as every point D is supposed to be viewed as a finite sequence? If I tell you what length I want, if I tell you what length I want, the ith component of the point D is just going to be f g I minus one D, where I is internal. This is a construction that you may have seen. That this gives you a coding, and you prove by induction on internal T that we have that this function is actually uh, that this is an onto this actually does the coding. In other words, for any sequence internal in the model of finite length, there's a unique D which actually works. Oh, I didn't say, I don't mean unique. There's some D uh, which actually works with this coding, actually gives you the actual function. Okay, and this is done by internal induction using uh, this idea. All right, let's not go into that in great detail, but anyways, this is a simple idea. All right, but now we need one more notion of recursion on omega, which we call omega recursion star, and this is that we can build a sequence of sets coded up. In other words, we can make it one more dimension and take cross sections. The cross sections can be, yeah, the cross sections can be defined by induction on along the non-standard integer by taking a first order formula in less than p epsilon and the set we've gotten so far. This is like arithmetic recursion in ordinary logic. It's like first order it's like arithmetic recursion. And this is proved analogously also. We take the least place you can't do it, and then you show you can do it there. Uh, now, yeah, I'm going to probably have to go over some time here in order to get what I want done here. Okay, now we're going to start building up L. So a DN set is a three-area relation. The first term is like numbers in integers. The second term is like points in P star of D. That P star of D is the dth uh, dth P closed number. The dth P closed number. P star was the enumeration of P closed numbers, and the third one is at one less. By the way, if D is a limit, then D minus one is D. By the way. All right. Where D is less than Cn and R is at the level of N. Uh, I guess ternary, yeah. Okay. And I'm going to have to explain what the point of this is. It gives rise to the structure alpha of R. It gives rise, there's a way to make this into a structure uh, of the right form. Uh, in other words, it's a three-area relation on this space with less than and the pairing function. Um, the back sections of R are of the form set of all E such that R of D1, D2, E for fixed D1, D2. Uh, and we say that R is pruned if the non-empty back structures are all distinct. Allow the empty set to occur as a section, back section, but I don't allow anything else to be. And that'll give us some nice extensionality. Now, let me tell you, we have to talk about what the point of this is. So we first work with the DN sets, but then the DN/L sets. Those are the real ones we care about, which are DN sets obeying a condition. A DN/L set represents the dth level of the constructible hierarchy of sets of ordinals, where D is less than C of n. And there'll be a unique DN/L set, a unique one, which will also be the unique DN plus 1 L set, since D is less than Cn. All right. There's a trivial start, the unique 0n L set. Remember, I'm coding up the constructible hierarchy of sets of ordinals via sets of ordinals, so to speak, in a nutshell. There's a trivial start, the unique 0n L set, independent of n. The crucial issue is how we build the unique D plus 1n L set from the unique dn L set. And for limits D, the unique dn L set is simply the union of the unique D prime and L sets D prime less than D. Sort of like how you build L in set theory, except this is flat. You got to be a little more careful. You have to be more careful. Now, suppose R is the unique dn L set. We read off the stage D constructible sets of ordinals from R as the family of cross sections of R obtained by fixing the first two arguments, i.e., such cross sections such cross sections, back sections, being the set of E primes such that R of I, E, E prime, that's the notation, what letters I want to use, where I less than omega codes a formula in the language for structures, alpha R, and E is less than P star D codes a finite sequence from 0 P star D. In the construction, these DNL sets have been pruned so that these cross sections are distinct. Specifically, the continuation of the unique DNL set R is defined in the obvious way using the semantics over the structure alpha of R, and then pruned so that the non-empty back sections are distinct. So that gives you the architecture of this constructibility construction. All right. Let R be a DN set. The R defined sets are the subsets of 0 P star D that are first order definable over alpha of R. Okay. Um, this refers to external first order definability. And this is external definability, but we need to make definition 4.10.12 internal to X. This requires a natural formalization of basic model theory of the alpha R internally in R. So I go through a thing here, which is just Tarski's definition of satisfaction as an omega recursion star. If you remember, I had the last form of omega recursion. Uh, and we have to use satisfaction. We have to use assignments. Now we don't use infinite assignments of infinite length really. we only care about a finite initial segment, okay? Um, so this is straightforward. How to do Tarski's definition internally in X. Uh, and have it nicely defined. Nice, a nice have sat nice. Okay, so here it is. So let R be a DN set. There's a binary relation set of phi of R, phi F, alpha of R. That's wrong. Alpha R phi of F in UN2 that satisfies the usual clauses for satisfaction for internal formulas. So this is just saying that I can do Tarski's truth definition internally. Oh, okay. And it lies in where it's supposed to be because this is because D is less than CN. Okay, and this is defined by an omega recursion star, if you remember following Tarski. Okay, now remember we're building up the constructible hierarchy of the hierarchy of constructible sets of ordinals, quote unquote, in a nice orderly way. And so let R be a DN set. We want to define the continuation C of R, which will be a pruned D plus 1n set, where the back sections of phi of R are exactly the R-defined sets. So this is like photo or FODO in the L hierarchy in set theory. And let me not go into great detail about this, but you can read this. Um, so the continuation is uh, is at the next level where uh, uh, we handle the assignments. We handle the first coordinate is a Gödel number of a formula. The second coordinate is the code of an assignment, and then how long is the assignment? Remember, we don't want infinite length. We use the largest subscript of the variables appearing in phi, which is just a convenient convention for when you cut it off. Uh, and and we the third coordinate. Remember, these are ternary relations. The third coordinate is carves out what the set is that what the set is. In other words, what the back section is, the back sections, and then we make sure, and then we have a convention by which we eliminate duplications, except we allow duplications of the empty set, which is convenient to allow and not a problem. Okay. Now R double star, yeah, I'm still doing this. R double star is the pruning. There's a way of pruning, meaning you take the least place at which something appears and throw the rest out. So there's an easy way to prune. It's not a it's not a recursion thing. It's an explicit thing. This is the pruning. Okay, so you always get a unique continuation. You always get a unique continuation, and it's a prune D plus 1n set. The back sections are exactly the R-defined sets, all of which lie in UN1. So the back sections, it's just like photo. The high back sections are exactly the R-defined sets that are not back sections of R. The low back sections are exactly the back sections of R. Yeah, so we make sure that we don't duplicate stuff that's already been handled in the previous stage. Those are not duplicated, and the new stuff is also pruned so that there's only one. So everything has one location. That's the idea. All right. So now let's define what we mean by being a good thing like this. I just defined what a continuation was. So we want so a DN set L is a DN set T with the following property. First of all, corresponds to the basis case. T intersect 0 and omega to the third is the empty set. We get nothing in there. So remember, everything any good starts at omega. Remember, our omega closed numbers start at omega. Okay, and then this is the successor case. We need to know that T intersect the previous space of stuff is the continuation of T of the previous one. So this is how we use the continuation. We insist that the actual T we've got has already got is already constructed right, namely that successors it's what it's supposed to be at the beginning. It's trivial. Okay, now it's already implicit in this definition that it limits. It's just the union. You see, there's nothing to add for that. The way it's set up, it's interesting. It's simple. That's already implicit. Okay. Now, how do I know that there is one of these things? I mean, otherwise, no good, right? In set theory, you just say it's a transfinite recursion, period. Here we have to be a little more careful. What are we saying? We want to say that, remember, these D sets have to be in U of N. They have to be nice. So again, we easily argue uniqueness and we get existence by saying, how far can I go? Where's the least place which I can't go that far in this construction? I don't have a DN set L of that length. And then I say, oh my God, a nice one, excuse me, a nice one. Then I say, oh my God, I can make a nice one further. I can do it. I can do it, but it won't be quite nice, maybe a little less nice because I'm quantifying over niceness. So I get, a little less nice. And then I can pull it back down because of indiscernibility. So indiscernibility is used again. So I get a unique DN set. It's pruned, and a DN set is also a DM set. That's just kind of notational. Uh, it's not really much. Um, okay, and then this is done by this again this argument of how you use indiscernibles with separation. Now, as familiar language from set theory, we now define what L of D is in brackets and L of D in soft brackets, in round brackets, in square brackets and in round brackets. L of D in square brackets is the unique DN set L, where n is least such that D is less than Cn. Well, that's just from notation. And L of round brackets is the set of all back sections in L of D. So L of D is the actual hierarchy structure in all of its glory. And L of D is only the contents that we're interested in, which is the back sections. And the whole L is the union of L of D, where D is in D star. Remember, D star is that initial segment, that cut of all the defined by the C's, the indiscernibles. Okay, now if A is a non-empty set, then $n of A is the location of A in L of D plus one. Uh, Now it's clear what I mean by the location. If you have something if you have a back section, it has a unique location, namely the first two terms, the number and the Gödel number of the formula and the code for the finite sequence that gives rise to that back section. Remember, which has to be unique because of the pruning. So that's what I mean by location. So we now define dollar sign. Dollar sign has to be defined ad hocly for empty set because we always say non-empty's been pruned properly and all that stuff. And that's zero. And then for all other A in the set, dollar sign N of A is C of N. Okay. In other words, only this stuff. Okay. So we get locations at each stage, right? The location of a set is actually you take the first place at which it appears, the first D at which it appears. Yeah, I mean, there may be something a little funny about the way I wrote that, but the basic idea is clear. So we have the theorem that L of zero square brackets is the empty set, L of soft brackets is the set consisting of the empty set, L of square brackets is contained in L of square brackets at a higher one. L of D plus one is the set of all L of D soft brackets is the set of all L of D defined sets. Now, this is interesting. This says basically that the back sections that I get in D plus one in the back sections of level D plus one are just the sets that are defined over the actual structure in one less place. And that's the neat thing about this. Uh, yeah. And then if D is the limit, then L of soft brackets D is just the union of the lower ones. And L of square brackets D is contained in lives in P star of D cubed. But this is obvious. And this is sort of obvious, all of this. Every back section of LOD is a subset of this for some E less than D. Okay, high back sections, locations. This is some cleanup work that's simple. Okay, so the actual relation, L of D is an actual ternary relation. It's a member of L of D plus one. And that's straightforward from the definitions because it's first order and this consists of the things that are first order over this. Okay, so A for A in L of Cn, the sup of A is less than or equal to delta N of A. Okay, we have that. Let's see what else. Uh, well, the dollar signs are actual locations, and since this hierarchy is compatible, it just grows. It agrees with everything lower. Doesn't make any difference if you use dollar sign N or dollar M if the set is good. So now we see what the dollar signs are in the last lecture more clearly. It's it's dollar sign N is less than Cn just in case you're in the constructible hierarchy up to Cn. Okay, now we move to the structure W that we used last week for section 11. And it has the dollar signs in it. $n is a mapping from set into this interval. And remember, it only achieves this endpoint Cn when the set is outside the scope, right? Outside of L C of n. Okay, and this is where uh, this is very close to where we started last time. Uh, Here we define the language. We have to modify the language to use the dollar signs instead of the U's. And and we convert everything. We do this language conversion. In other words, these dollar signs have pack more power than the U's, but they're the same because I mean, but they it's it it's meant to define the constructible substructure inner model of constructibles. Uh, I don't think there's anything here that's too important. Yeah. All right. And this is so that's how the separation works. We just changed the language in a simple way. And here's how the indiscernibility works. It's no different. It's just converting the old indiscernibility, which had U's, now with dollar signs. And now we get finally this theorem 41027, which is the exact place where we started last lecture. We started the last lecture right here. If you recall, we fixed the delta n so they were onto. Then we started to define a model of set theory. No, yeah, a model of set theory. EP, capital EP. We defined an epsilon relation. We showed that we got models of ZFC. Then we got models of ZFC with large cardinals inside. That was last time. And then we're done. Okay, so just to review for a second, I'm almost done. We started with the end of section 4.9, which looks like this. No constructible sets, no dollar sign. We started like this, and we started with a K, and then we got rid of the K. Then we got rid of the K by going to a first order form, getting rid of the fact that the C's were cofinal, which is fine. It turns out not to be important that the C's be cofinal. And so we got here. With the U's, but no K. Oh, this has a K. Yeah. Then we got rid of the K. I mean, I did it slowly by the first order, by the compactness number first order logic. And then we went ahead and did the whole development of L, like in Gödel's monograph, except we had to do it flat and had to make sure that we could do it within this structure. Within this structure, do L, and then wind up with this. Which is the beginning of the last lecture. All right, Andreas, I'm done.
Great.